Hello and welcome to Starborn Science. Today we will go over my UV Absorbance Meter. I'm gonna go over it really quickly over here. We have an LED that's driven by square pulses in a set frequency and duty cycle that's emitting in ultraviolet in about 380 nanometers that shoots a beam of ultraviolet light which passes through a special vial called a cuvette. I don't speak French, whatever. That in turn gets detected by a reverse biased LED that acts as our detector, which then gives an electrical signal to our meter that gets translated in millivolts. Now there's a base over here for the cuvette. That's really important, so because our measurements are consistent, and yeah, that's really the heart of the machine. And here we have the formula that calculates absorbance. In this case we are measuring volts. To be accurate, we're measuring millivolts. And the absorbance is a pure number. It's a dimensionless quantity given by the calibration blank voltage, which is something that we set our meter at before we make the measurements, divided by whatever measurement we get. So this is the voltage of the blank and this is the voltage of the light passing through the sample, divided, and this is the logarithm value of that number, which gives us the absorbance value, and that's how we calculate the absorbance. So enough with the boring theory, people. Let's get into the build, which is pretty damn simple actually. This is the meter. This is our pulse generator set at 500 Hz and 43 duty cycle. And as you will see, like even with professional instruments, the voltage at first isn't quite stable, nor is it set at 500 millivolts as I've set my meter to be. It needs a warm-up time, which is about 2 minutes, 3 minutes, give or take. So I'll wait for it to warm up and I'll be back. And so it has kind of stabilized now. And I have written down some serial dilutions, meaning each time per measurement we half the dilutions, and since it's a kind of an eye candy, we will be using fluorescein. It's potassium salt in particular, to measure the absorbance. So this is a cuvette. This is made from quartz and light goes in from this side and out from this side. You can see I have this marked as I wanna install this the same time always, and I know the red side is the right side and the black side is the left side, and that way I always put it in the same way, and that minimizes the error margin. So yeah, that's why it's marked. So I filled the cuvette with 1 molar of fluorescein, 1 molar solution, and keep in mind 1 molar of fluorescein is a lot. It's really concentrated. So now I'm gonna go ahead and replace the distilled water with which we calibrated at 500 millivolts and replace it with the fluorescein. And we should see an immediate drop in transmitted light. Which of course we do. And I'm gonna take you with me here. Because I want you to see the beam. As it passes through the solution. Stupid heatsink is in the way. There, this is the best I can do. So very little light reaches the sensor, and we have a reading of 2.2 millivolts. So 2.2 millivolts. And so this is half a mole of fluorescein, and my meter went off. But I likely remember that it was 30.9. Yep. And we are at the 0.625 molarity mark, and we're getting 315 millivolts. But I actually stopped here for a moment to show you the beam that now passes through all of the cuvette, which in my eyes is really beautiful. see this is where it enters from. Can't really get a good shot, but this is where it exits from. And over here is the path of the beam from the side. This is Lambert's law, and it's a very beautiful equation. However, there are a few problems. And first problem is that our beam, instead of a professional colorimeter or photometer or spectrophotometer, is that we do not have a coherent beam, meaning a very tight beam, or a monochromatic beam, as in a laser or a beam that has passed through a monochromator or a prism, and we have an LED. And our LED emits light both at the violet range of the spectrum and the ultraviolet range of the spectrum, and we can't really work with that. So we also do not know epsilon with this symbol, which stands for molar absorptivity, and you do not wanna be checking chemical databases for 6 hours every time you're making a measurement. So how do we fix this? Well, there's a fix. Allow me to explain. Now, luckily for us, there is this beautiful formula. Let me explain. Of course, our given objective is always to find the concentration of an unknown solution, either using the Lambert's law, or should I call this the since it doesn't have a name, I'll call it the whiskey Lambert's law. That wasn't good. That wasn't good. So M is called slope in mathematics, and I'm gonna keep it simple and tell you that it's just the rate of change between our measurements. Of course, A is our absorbance, which we can measure, so it's one of our data points. M is something that we can calculate through our calibration curve, so it's again derived out of our data. And B is something that we can also calculate through our data, and it's called background absorbance, and its value, a very tiny value, that is the absorbance at zero concentration. The absorbance basically that our blank sample has, the calibration sample, the distilled water in this case. So M, our slope, can be derived from our calibration data by this formula. Delta stands for difference, and A stands for absorption, and C stands for concentration. Now, given that, of course, we have our absorption and concentration through our calibration curve, we plug our values in there, and we need our calibration curve in this one because we need to choose linear values, or the most linear values we can have, and the more values we use, the better. So we can do it just with 2 values, but yeah, you can use more for accuracy, and that's how we calculate n. So that's that. And according to my notes, this is the value of m. So this is our slope. And since, of course, again, we have all these values now, we can also calculate B, which is always a tiny number. And according to my notes, B is this. So now we have every number we want. So let's go back to our initial equation and plug all these numbers in. And this is what we get. Now let's solve for C, the concentration. And this is the final form of the equation. So, in order to calculate the concentration, we just make a measurement of a known compound that we have its calibration curve, convert it into absorbance by dividing it with its blank measurement, getting the logarithm of that number, plug it into our equation over here, and getting its concentration. So this is a really powerful tool to have in your laboratory, and as you can see, you do not need super expensive equipment to do that. You do not need a $5,000 spectrophotometer. Well, of course, if you are in the FDA, you probably need to, but in a home lab, that's perfectly fine. So it's not super accurate, but it is accurate enough to monitor reaction progress, complexation, filtrations that you do not know the concentration of the filtrate, solutions you forgot about and you didn't, or that may have evaporated over time, and their concentration changed, and so on and so on, given that of course you do have the absorption values and the calibration curves of these compounds in the solvent that they are in, of course. And again, this is working in the ultraviolet range. In the ultraviolet range, meaning the peak emission of this LED is around 385 nanometers. So this mostly detects absorption in this range. Now, many compounds do absorb light in this range, but it's limited in this range. Now, you sure could pull off a trick to make that LED changeable. Yep, you could. You also could use a lamp that does produce light in all spectral ranges, from near infrared to deep UV, and use a prism, although that at this point would not be a photometer, it would be a spectrophotometer. But yeah, this is not that. This is a fixed wavelength spectrophotometer, if you will, or a ultraviolet photometer. Call it what you will, it's the same thing. So, that's about it. In any case, people, that is what I wanted to share with you. I hope you liked it. I hope you learned something. Like the video if you liked it. Don't if you didn't. Keep dreaming, keep exploring, and I will see you on the next one.